Well, hello everybody. I'm so glad to be with you. And I'm sitting in my summer house, and there I had a meeting with Carla and Ruggiero many years ago. It was a fine meeting and memorable too. And I thought it natural to speak from here to you. I start immediately sharing the screen and putting in the lecture and sharing it again and put on the kind of display here. And now we should be started. And it's just a talk about entanglement and called Entanglement is Physical Reality. That is in a three-dimensional world. And I shall just put on so I have the pointer and can operate with that. So the two main figures here is Mendeleev and Mario Sophus-Lee. And I was in St. Petersburg last year to celebrate 150th anniversary of Mendeleev. And then it was 148 years since Mario Sophus-Lees thesis över en klasse geometriska transformationer. And next year it will be 150 for him too. That should be celebrated. So both were involved with nature's language, you could say, and particles didn't exist for any of them. And linguistics were the interest of Mendeleev, and also a kind of prototype for his idea about particles or the atoms. And the game of Lee is geometry. And he's dealing with a phase transition between straight to round, if you simplify the issue. And from the interior surface of the maximally extended cube to the outer surface of the maximally contracted sphere, there is an interstice, and that is the kind of playground for the transformations. There you have dynamics, whereas both the cube and the sphere are static. The sphere, for instance, could represent the dark mass, perhaps. And that's fascinating per se. So the geometry is about transforming a flat to a spherical space, and you do that by the infinitesimal generators. And the, so to say, bottom line of Lie transformations is that they do it in the infinitesimal scale. So the global symmetries actually are retrieved in the smallest point or smallest area, a Lie neighborhood that you could find in the microscopic scale. The root space diagram of the infinitesimal transformations is A2 if you have them over the complex numbers, but the real space is single valued, so you have to double the diagram instead, so you get A3, and then you don't only have a flat representation, but you have a spatial representation, three-dimensional, and actually you could connect it to a lattice, and that lattice could be in hexagonal symmetry, but combining the root space vector instead orthogonally. You also have an orthogonal symmetry that you can connect, and I come back to that, but there are kind of various geometries in the A3 root space diagram. And the standard model, that rests upon the idea of particles as point-like and in a way structureless, but it's a bit problematic because both gluons and quarks and electrons and whatever are just points, and it's hard to see how they could enact a difference between themselves or at large. But anyhow, if you consider them as points, you get the standard model in order to accommodate the real spectroscopy you see. But least ground element was the straight line of length equals 0. And although equally small as an infinitesimal point, it has the difference of being a line, so it can be connected in the shape of partial derivatives directly. So you can make differential equations prima facie, and by that you can do a lot more than rotations, as he wrote himself in his thesis. And what you can do is in terms of tangential spaces. So we see here that these tangential spaces really operate upon the surface of, in this case, the sphere. And it's so good that the root space vectors of Lie transformations are tangential in relation both to the proton and the neutron surface focus points. So you can do transformations then both inside the nucleon, here hemispheric, and on the surface of the nucleon, but also outside the nucleon by connecting these root space vectors. And that actually is the idea of the presentation here. But I show you what you can do with the inside, because when they reach their endpoints here, the root space vectors, they form new possible major semi-axis of ellipsoid transformations. And that goes way out. So you get angular momentum in terms of step outside the nucleon you have. And then if you draw the line from the endpoint to the center here, you have a new major semi-axis. And then of course it should be volume preserving and symmetry preserving, so you get ellipsoid. And that is actually what Professor Santilli is talking about when he talks about extended bodies of precisely this configuration. I just show you some equatorial or flat projections of some transformations you can do this way, and which happens to replicate then the eightfold way super multiplets. And you also get the various kind of plus, minus, and so forth and so on. And you get the mass directly by multiplying inversely proportional to the proton unit radius. So we go on to the mesons, which are intermediary differential bodies, you can say, between a baryon transformation and its decay finally into leptons. And they are very short-lived, most of them, but they follow the symmetric SU2 times antisymmetric U1, and you can, by calculating that way, also make good replications of the mesons. And I don't go further into that because on the surface, you can try to connect the hexagonal, but you can also find the orthogonal, which have either on 180 degrees or 90 degrees angular orientation, and connecting them, you get the muon geometry or geodesics, which in relation to the unit proton radius has inertia of 105.59, and that is very close to the real value. But when you try to make a surface representation of the hexagonal vectors, they really don't form any, but they form this threefold structure instead in the inside of the nucleon, and that happens to correlate to the tau, both mass-wise and in terms of symmetry, because the tau, although a lepton, has actually the symmetry of SU2 times U1 of the mesons. So it's an intermediary form. And here we show some other leptons, for instance, neutral pion that turns out to two gammas, and they show this entangled, so to say, opposition that comes out for every quantum appearance, let's say spin or polarization. And the other I'll show is the muon decay. The muon goes over in an electron geodesics and leaving then an identical balance of spins, antineutrino, neutrino, muon, electron. But the real contents here are what happens with the external continuation of the root space diagram. And then we can see that they connect to what is a continuous lattice of one octahedron, two tetrahedron that we call isotropic vector matrix, and is equally endless as a cubical lattice and continuing the same element, namely 12 unit length vectors in every identical or single module of itself. And how to find the way of then making a continuous path in this system. You have to stash them in an ordinary form. And I show you here the module that you have to use to pack it. And this has a flat bottom, which is important. But of course, you need a flat roof also. And you can repeat this here. The singlet module, as I call it, and also called an electron singlet, are packed into the Euclidean space chaperone modules and can pack into a Bohr orbital distributed module here. And then, of course, if you pack this module, you find that it will form a rhomboid-like kind of bottom plate that in turn can be packed like this. If you pack this, you find this kind of tessellation, and it's not exactly space filling because there are some loopholes in it. And how to overcome that? Yes, that is by the roof, because in order to have a roof that complies with the bottom plate, you need to add some mid columns here. So you get 28 of them. And you also need to add one extra 5 of them, and then complementing with the 1 to the 152 there, you get 2 halves of 153 such constituents, and that is with the 12 straight lines, the proton-electron mass ratio, and packs into a real space-filling tessellation. But the problem was this extra, and if you put the extra one here, it obliterates. So really this kind of tessellation is abortive in the way that it becomes overcrowded. So one needs to find another, but I show the principle that you have a bottom module, you have a roof module, and they combine so that they form what perhaps could be called a transition apparatus in analogy with the ribosome translation apparatus of biology, which is also a two-story building that, so to say, enfolds its creations or constructions. You can see that this can be formed together either with a central hole or without central hole, and that relates to the two forms of hydrogen, as I will come back to. It also tells you a bit about that if there is a space-filling brain that is flat, that means also that it's thick to a similar degree, because it can't be just empty space between these. This would be paradoxical in a way, but they must fill also in this projection vertical direction. And we see that also in the crystal formation of atoms that mostly are cubical with, of course, flat surfaces everywhere, but even hexagonally crystals are flat roof, flat bottom prisms. You can't really get three-dimensional hexagonal expansion. It turns flat. It stays flat. Anyhow, we must find another module, and then if you let them collide or compress sideways, there will be created two new modules, which has a central corner defect here, and thus, but they can tessellate with each other. But in order to find a roof to that, we end up with this kind, and we have the same 153. We can show it again here, that in the primary constitution it will form this kind of tessellation, which can be space filling. But if we add this roof again, you will have two ways of combining it. And you can either combine it without central hole, which would be the 1H, and form the H2 molecule. So H2 would mostly be composed by 1H, and you can also stash them to a central hole here. This is shown here with a singlet cubicle or qubit packs to a neutron, and if they are oppositely turned, they can form two neutron, which would have alpha form, but just two mass. And the SO3 coil here is an electron singlet, and forms the protium distribution, you could say, of the electron. And if you try to squeeze two similarly oriented neutrons to each other, one of them will turn to to a protium, and thus together with form deuterium. So it's a system that then generates the symmetries shown a bit better here. So the neutron combined with the proton will form 1H2 deuterium, and if you stash then another neutron upon the deuterium, we will have the 1H3 helium hydrogen, whereas if you take a charged proton on top of a deuterium, you get 2 helium-3. And of course, if you combine 2 deuteriums, you get an alpha particle, which is ordinary helium. And this ordinary helium, like all the others, can be tessellated in a space-filling way. And these modules then can be stashed and combined or superposed, as it were, towards each other, forming, for instance, 3 lithium-6 here. If you combine an ordinary alpha with an ordinary deuterium, but if you combine just with a charged 1H1, you get 3 lithium-5 instead. And yeah, you can see you can get 2 helium-5 also, for instance, by putting a neutron on top. And this is the ordinary beryllium-4, beryllium-8. So you can go on like this, and these modules are, you could say, the Lego variety, which is fine-grained. The bigger the molecules or the atoms, of course, it's better to try to have some simpler representation, and we can call them Duplo. Yes. And then creating lithium is easy. Beryllium, boron, carbon, fascinating with 4 binding sites, but also redistributable to 3 or 2 bindings even. That depends upon how you stash these to each other. And we have the nitrogen, we have the oxygen, we have the fluorine, and you can see that it is only 1 binding site and becomes very hungry, you could say, so it's very reactive. But then suddenly when it's filled up to neon, all the alphas are filled, so there are no vacant binding sites, so there can be no binding. And if we go on with the next period here, the 3rd period, we see that sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon are in line, and sometimes they need a little neutron here to be in the best shape. All these are the most stable varieties of the respective. But argon is an exception because this is the astrophysical one, which is all filled alpha, but the earthly argon is formed by decay and has some neutrons also. But that doesn't change the fact that all the alphas are filled, so it can't react otherwise under special conditions than artificial ones. So we can continue this way of stashing modules upon each other, and kalium, calcium, or potassium, calcium, or scandium and titanium, and vanadium and chromium and magnesium and iron can all be replicated quite simply, and they will tessellate space-fillingly. And after iron, it's not possible anymore, but one can do a lot with these. For instance, potassium has a binding site here, but chlorine has, as we saw, a vacuum instead, so they will join each other very eagerly and create potassium chloride in various ways. And for instance, 4-valued carbon can also bind to chlorine and create carbon tetrachloride. And I show, and you can really find a lot of such. And here I show some of the carbon on the burning reactions that occur in the stars. And I just show them rapidly. Carbon burning, neon burning, and oxygen burning. And now it's becoming large atoms, larger, so it's better to have them represented by Duplo bricks. But still, you can go on and find a lot of what happens. And in the laboratory, you can stash alpha chain alphas on each other. So from 24 chromium 48, you stash till 26 iron 52, and you go on, and thus you can come up to zinc and further with this artificial method. And also you can find beta chains instead, deuterium exchange, which serves to increase or reduce the number of charged particles. So this is just an example. And again, we say that these transactions can go on up till iron, but what happens then? Well, then we have the neutron capture, and this is very important that after iron, what happens in stars depends almost totally upon neutrons. So there has to be a colossal production of neutrons in the stars to let atoms be larger, as it were. And the slow process is that, as we saw, if one neutron would be squeezed into another neutron in the same orientation, it will transform to a deuterium. So that means that it loses one neutron, but it increases mass instead by doubling mass in the other. So you have the same mass, but you get another atom because of increased charge. And you can get up to strontium and further on by combination of beta decays, beta minus as we would call them then. And neutron sources we have in stars, and these are some reactions that are very productive and gives a lot of neutrons. So neutron is, you can say, the building elements of the atoms that we have spontaneously after iron for the most part. But after iron, we must instead show then how it goes on, and it's like an extra neutron in a thus unstable iron and seeks up a vacant one and turns it into a deuterium. And that happens in some isotopes that are thus unstable. And you can see that we can line up a lot of isotopes with increasing or decreasing neutrons. And these would of course be unstable, but you can even have them without neutrons at all and just have the charged particles. So it's a system that in its replication here do reproduce what we see in reality, and that also uses the same mechanisms of, so to say, increasing atom number. So the slow neutron capture goes on as sometimes very troublesome stairway that brings you systematically up the hill and to krypton. And krypton again has full alphas. So that will be then, because he was a free binding site in bromine. And here we get an unstable 36 krypton 85 that then goes to the next period. You can see the difference. This is the slow neutron capture, and it takes you as far up as bismuth, but bismuth goes by an alpha down again. So the most stable you can get by the slow stack way is lead. And how we form the other ones, because lead stops here, well, that is by the rapid. And the rapid is a colossal amount of neutrons that creates a lot of isotopes from uranium. And then it goes down in steps of alpha to fill up atoms further down, as far actually as down to scandium, quite far below. So far we have only had the fourth period completed. Krypton 84, which is the most stable krypton, has a very harmonic shape and has full alphas and is thus inactive. But to fill the fifth period, we have ample space in the orbital margin, as it were. And when we come to the sixth period, we can fill the 32 alpha particles that it needs, because it, then we can also include the lanthanides. That is a deficiency in the ordinary, that it can't really fill the gap here in the sixth period for the rare earths. But that can easily be accommodated within this orbit or margin. And by filling out internal the lower orbits, because the outer will always be 4, 8 alphas. So this is the same with actinides. It also can be amply, and to fill up these margins, there will be increased neutron excess. We can just stop by showing the kind of ground module in a side projection instead. And we see the columns here, and the columns, they replicate how many alphas shall be introduced in each new layer. But I don't go into this any further, but we can ask finally what bearings this has to the topic, and we can see that this is really entangled things. They are entangled, and they are entangled because they are superpositions of each other. And if you have superpositions, you have quantities that already from the start are, so to say, identical in the way that their decay are entangled as superpositions when the creation begins. So they are automatically coupled in the way that entanglement is. Either it's a pair, which is the usual experimental condition, or it's a group, for instance, and have a larger decay. And that is self-evident in a space-filling three-dimensional world. But even in the fourth or fifth dimension, it's principally the same, that if they are superpositions from the start, they will also be entangled if they part. So I think I stop now my lecture here, and that I do here. And now I thus say goodbye from Summer House, and then stop recording.